Hold a single grain of sand at arm's length toward the night sky. That tiny speck blocks a patch of darkness that seems empty. It is not. James Webb stared at that emptiness for 12 hours and found 800,000 galaxies hiding inside it. 800,000 complete worlds, each containing billions of stars, each existing at different moments across 13 billion years of cosmic history, all of them invisible to every telescope that came before. But that was just the beginning of what should not exist. A galaxy blazing with starlight only 280 million years after the Big Bang. That is like a newborn building a city before learning to crawl. A black hole feeding 40 times faster than physics permits, gorging on matter while breaking every law we calculated. Another black hole weighing 10 million suns, racing through space at 2 million miles per hour, fleeing its home galaxy, and leaving a trail of newborn stars 200,000 light-years long. We measured the universe at 14 billion light-years across. We were wrong. It spans 93 billion. And the two methods we use to measure how fast it expands give two different answers. Something fundamental is missing from our equations. Something we cannot yet name. The telescope that revealed all this floats 1 million miles from Earth, colder than Pluto, its golden mirrors collecting photons that left their sources before our planet existed. Everything we believed about the cosmos just shattered. Prepare for a journey through revelation beyond comprehension. We begin. There is a machine floating in the darkness right now. As you breathe, as you listen, as you let your body settle into stillness, this machine drifts through the cold void nearly 1 million miles from Earth. It hangs at a special point in space where the gravity of our planet and our star balance perfectly. Scientists call this place Lagrange Point 2. You can think of it as a cosmic parking spot, a place where something can stay forever without drifting away. The James Webb Space Telescope chose this location for one simple reason: darkness. To see the oldest light in the universe, you need absolute cold. You need silence from heat. You need to hide from every warm thing that might interfere with your vision. At Lagrange Point 2, the telescope floats in the permanent shadow of Earth. Our planet blocks the light of the sun. The telescope never sees direct sunlight. It never feels the warmth that bathes our world every morning. Instead, it exists in a kind of eternal night. A frozen twilight where temperatures drop to nearly negative 370 degrees Fahrenheit. That is colder than the surface of Pluto. Colder than almost anywhere humans have ever measured. This extreme cold is not a problem. It is the entire point. You see, James Webb does not look at the universe the way your eyes do. Your eyes detect visible light, the rainbow of colours you learnt as a child: red, orange, yellow, green, blue, violet. These are the wavelengths your brain has evolved to see. Because our star pumps out most of its energy in this range, it makes sense for creatures living under sunlight to see sunlight, but visible light tells only part of the story. James Webb sees in infrared. This is a kind of light your eyes cannot detect at all. You feel infrared as heat. When you stand near a fire and sense warmth on your skin, even with your eyes closed, that warmth is infrared radiation touching you. Everything warm emits infrared. Your body does. Your coffee cup does. The walls of your room do right now. If your eyes could see infrared, the world would glow in strange new ways. Hot objects would shine bright. Cold objects would fade into shadow. The telescope's instruments must be kept incredibly cold, because warm detectors create their own infrared glow. Imagine trying to photograph the stars while someone shines a flashlight in your camera lens. That is what would happen if James Webb's sensors heated up. They would blind themselves with their own warmth. So the telescope hides in shadow, wrapped in a sunshield the size of a tennis court, cooling itself to temperatures where metals become brittle and ordinary machines would shatter. Why does infrared matter so much for seeing ancient light? Here is something wonderful to hold in your mind. When light travels across the universe, Space itself stretches. The universe is expanding. Not like a balloon being inflated with galaxies painted on its surface, though that image helps. More like the fabric of existence itself growing larger every moment. As space expands, it pulls light waves along with it. Light that began its journey as ultraviolet or visible radiation gets stretched into longer wavelengths. By the time this ancient light reaches us after travelling for billions of years, it has shifted completely into infrared. The oldest light in the universe is invisible to ordinary telescopes. It has been stretched beyond the rainbow your eyes can see. Only an infrared telescope can catch it. Only James Webb can witness the birth of galaxies. The telescope's primary mirror tells a story of engineering genius. 21 feet across, it consists of 18 hexagonal segments fitted together like a golden honeycomb. Each segment is coated with a microscopic layer of gold. Not for beauty, though it is beautiful. Gold reflects infrared light better than any other material known to science. The mirror collects ancient photons the way a bucket collects rain. Each segment can be adjusted by tiny motors, tilting fractions of a hair's width to focus the entire array perfectly. This precision allows James Webb to see objects 100 times fainter than what the Hubble Space Telescope could detect. Hubble orbited Earth for over 3 decades, giving us iconic images of nebulae and galaxies and cosmic wonders. But Hubble saw primarily invisible light. It could dip slightly into infrared and ultraviolet, but it could not reach deep into the wavelengths where the oldest light hides. Hubble was like a person with excellent daytime vision. James Webb is like someone who can see in complete darkness. There is something strange to consider here. Some scientists have suggested that the precision required to build and deploy James Webb pushed human engineering to its absolute limit. The mirror segments had to unfold perfectly after launch. The sunshield had to deploy flawlessly through hundreds of steps. Any single failure would have ended the mission. Yet everything worked. Some researchers half-jokingly call it a miracle of probability. Others wonder if our technology has reached a threshold where such achievements become expected rather than exceptional. The debate continues quietly in engineering circles. How close were we to failure? How much luck played into success? What remains undisputed is what the telescope found once it opened its golden eye. In the months following first light, James Webb began returning images that made astronomers pause. Objects appeared where none were expected. Galaxies shone brighter than any model predicted. Black holes existed that should have taken billions more years to grow. The universe revealed itself not as we imagined it, but as it truly is. Stranger. Older in some ways, younger in others, more violent and creative than our simulations ever suggested. Every photon James Webb captures has travelled across expanding space for inconceivable distances. Some photons started their journey when the universe was only a few 100 million years old. They have been falling toward us ever since, stretched by time, cooled by expansion, carrying information about a cosmos we have never seen before. The telescope gathers these photons one by one, counting them, recording them, building images from whispers of light that left home before Earth existed. You are living in the first generation of humans to witness this. The first generation to see the universe as it looked in its infancy. The telescope drifts in its frozen orbit, its mirrors drinking starlight, its instruments translating heat into knowledge. It asks questions with every observation. Where did galaxies come from? How did the first stars ignite? What forces shaped the cosmos in those early chaotic years? The answers are still arriving, photon by photon, image by image. And what they reveal will reshape everything we thought we understood. Hold your hand up to the night sky. Extend your arm fully and look at your smallest fingernail. The area it covers seems tiny, a speck against the vastness above. You might think that patch of darkness contains nothing, just empty black space between the bright stars you can see. You would be completely wrong. In that fingernail-sized patch of sky, there are thousands of galaxies. Not stars, galaxies, each one containing billions or trillions of stars, each one a universe unto itself, filled with planets and moons and mysteries we will never personally explore. When James Webb turned its golden mirrors toward a specific region of space for its first deep field image, it stared at an area roughly this small. The telescope collected light for 12.5 hours. Photons trickled in one by one, accumulated, built up slowly like snow falling on a winter night. And when astronomers assembled the final image, they found themselves looking at something that challenges human comprehension. The target was a galaxy cluster called SMACS 0723. It sits about 4 billion light-years from Earth. That means the light in the image left those galaxies 4 billion years ago, long before our Sun even existed. The cluster itself contains hundreds of galaxies bound together by gravity. Their combined mass is enormous, so enormous that it bends the fabric of space around them. This bending creates something remarkable. A natural telescope. When light from even more distant galaxies passes near the cluster, the curved space acts like a giant lens. It magnifies and distorts the background objects, stretching them into arcs and smears of colour. Some galaxies appear multiple times in the same image because their light took different paths around the cluster. Einstein predicted this effect over a century ago. He called it gravitational lensing. James Webb uses massive galaxy clusters as cosmic magnifying glasses, seeing objects that would otherwise be far too faint to detect. Behind SMACS 0723, the telescope found the real treasure. Galaxies beyond the cluster, stacked in layers of distance. Some appear blue in the processed images, indicating they are relatively nearby and their light has not stretched much. Others glow deep red, signalling extreme distance. Their light has travelled so far, stretched so much by cosmic expansion, that it arrives in wavelengths far beyond what visible light telescopes can see. The faintest objects in this image reach what astronomers call magnitude 31. That number represents brightness. To understand how dim this is, consider that the faintest stars your naked eye can see under perfect dark sky conditions are about magnitude 6. Each step of 5 magnitudes represents a 100-fold decrease in brightness. Magnitude 31 objects are roughly 100 million times fainter than what your eyes can detect on the clearest night. James Webb saw them anyway. Every smudge and dot in the deep field is a galaxy. Nearly every speck of light that is not an obvious nearby star with its telltale diffraction, spikes, represents an entire stellar city. Astronomers counted roughly 10,000 galaxies in this single image. 10,000 complete systems of stars, gas, dust and dark matter, all visible in a patch of sky you could block, with a grain of sand held at arm's length. Now consider the entire sky. There are over 40,000 square degrees across the celestial sphere. If every patch contains similar galaxy density, and observations suggest they do, then the total number of galaxies in the observable universe exceeds 2 trillion. That is 2,000 billion. A number so large it loses meaning. We cannot picture 2 trillion of anything. We can only accept it as a symbol of impossible vastness. Here is where the image becomes even more strange. Before James Webb, astronomers expected to find a certain number of bright galaxies in the early universe. Their models predicted slow, steady galaxy growth over billions of years. The deep field revealed something different. There were 10 times more bright early galaxies than models suggested. The universe was not empty and quiet in its youth. It was crowded and active. Galaxies appeared faster, shone brighter, and existed earlier than anyone anticipated. Some scientists have proposed unusual explanations for this excess brightness. A few suggest that the first galaxies formed populations of supermassive stars, objects hundreds of times heavier than our Sun, that burned with extraordinary intensity. Such stars would live only a few million years before exploding, but during their brief lives they would outshine entire modern galaxies. These supermassive stars remain theoretical. No one has confirmed their existence. Yet something made early galaxies brighter than our physics predicted. The debate continues among astronomers. Are our models of star formation wrong? Did the early universe convert gas into stars more efficiently than galaxies do today? Were conditions different in ways we have not accounted for? Perhaps dark matter played a larger role than expected, pulling gas together faster into denser concentrations. Perhaps feedback mechanisms that slow star formation in modern galaxies were weaker or absent back then. Each answer raises new questions. What remains certain is the visual truth of the image itself. Look at a deep-field photograph, and you are seeing cosmic history laid out before you. Nearby galaxies show the universe as it appeared a few billion years ago. More distant galaxies show earlier eras. The farthest red smudges capture light from when the cosmos was less than 1 billion years old. Time is encoded in distance. Every layer of depth is a layer of the past. The image also reveals the large-scale structure of the universe. Galaxies do not scatter randomly. They cluster together in groups and chains, forming a pattern scientists call the cosmic web. Filaments of galaxies stretch across hundreds of millions of light-years, connected at nodes where massive clusters sit. Between the filaments lie vast, empty voids where almost nothing exists. The universe has texture. It has architecture. And SMACS 0723 sits at one intersection of this grand design. 12.5 hours of observation. One small patch of sky. 10,000 galaxies revealed. The Hubble Space Telescope needed weeks to achieve similar depth. James Webb accomplished it in half a day. This efficiency means astronomers can survey larger regions faster, building an ever more complete map of cosmic history. Each galaxy in the image carries its own story. Stars being born in some, stars dying in others, black holes feeding at galactic centers, collisions unfolding over millions of years, lives being lived on planets we will never name. The diversity staggers the imagination. No two galaxies are identical. Each represents a unique outcome of gravity, gas, time, and chance. And this is just one image. James Webb has captured hundreds more since operations began. Every observation adds galaxies to our census, discoveries to our knowledge, questions to our growing list of mysteries. The universe keeps revealing itself, deeper and stranger with every photon collected. Light has memory. Every photon carries within it a record of the journey it has taken. When you look at a star tonight, you are not seeing it as it exists right now. You are seeing it as it was when the light left its surface. The nearest star beyond our sun sits over 4 light-years away. That means the light you see departed 4 years ago. You are always looking backward in time when you look up. James Webb takes this principle to an extreme that borders on the mystical. The telescope sees light that has been travelling for over 13 billion years, photons that began their journey when the universe was barely 300 million years old. These photons have crossed nearly the entire observable cosmos to reach the golden mirrors waiting at Lagrange point 2. They arrive stretched, changed, transformed by a process called redshift. And understanding redshift is understanding how we turn a telescope into a time machine. Imagine a wave on the ocean. It has peaks and troughs, a distance between each peak called wavelength. Light works the same way. It moves in waves. Different wavelengths create different colours. Short wavelengths appear blue or violet. Long wavelengths appear red. Your eyes detect wavelengths between roughly 400 and 700 nanometers. This range is the visible spectrum. The rainbow. But here is what happens when light travels across expanding space. The universe is not static. Space itself grows larger every moment. Not just the objects in space moving apart, but the actual fabric of existence stretching like dough being rolled thinner. As space expands, it pulls on everything inside it, including light waves. A photon travelling through expanding space finds its wavelength stretched. What started as a short blue wave becomes a longer green wave, then yellow, then red, then infrared. The longer the journey, the more the stretch. Astronomers measure this stretching using a number called redshift, represented by the letter Z. A redshift of 1 means the light's wavelength has doubled. A redshift of 2 means it has tripled. A redshift of 10 means the wavelength is now 11 times longer than when it started. MUMS Z14, the most distant galaxy James Webb has confirmed, has a redshift of 14.44. Its light is stretched by a factor of over 15. Think about what this means. A galaxy emits ultraviolet light at a wavelength of 120 nanometers. That light travels for 13 billion years. By the time it arrives at James Webb, it has stretched to nearly 1900 nanometers, deep into the infrared range. It has shifted completely beyond what human eyes can see. It has moved beyond what most telescopes can detect. Only an infrared telescope operating in the cold darkness of space can capture it. This is why the Hubble Space Telescope could not find the earliest galaxies. Hubble operates primarily in visible light and near-infrared wavelengths. It can see wavelengths up to about 1600 nanometers. Galaxies with redshift values above 7 emit most of their light beyond this range. They are invisible to Hubble, not because they are too faint, but because their light arrives in colours Hubble cannot see. They exist in a spectrum beyond Hubble's vision. James Webb was built specifically to solve this problem. Its instruments cover wavelengths from 600 nanometers all the way to 28,000 nanometers. This enormous range captures light from galaxies at any redshift up to about 20. Beyond redshift 20, even James Webb struggles, as the light shifts into wavelengths its detectors cannot measure. But within that range, the universe opens completely. Here is the beautiful part. Redshift tells us distance, and distance tells us time. When astronomers measure a galaxy's redshift, they are measuring how much the universe has expanded since that light began travelling. Higher redshift equals more expansion equals greater distance equals farther back in time. A galaxy at redshift 6 shows us the universe as it looked 12.7 billion years ago. A galaxy at redshift 10 shows us the cosmos at just 480 million years after the Big Bang. Each increment backward in redshift is a step deeper into cosmic history. The expansion itself is accelerating. Dark energy drives this acceleration. We do not know what dark energy is. We only know it exists because we can measure its effect. It pushes space to expand faster and faster. Galaxies far from us are receding at speeds that exceed the speed of light. This does not violate Einstein's relativity because the galaxies themselves are not moving through space faster than light. Space between us and them is growing faster than light can cross it. This creates a strange situation. Some galaxies are moving away so fast that their light will never reach us. The space between us and them expands faster than light can travel across it. These galaxies are beyond what we call the cosmic event horizon. They are forever invisible. We will never see them no matter how long we wait or how powerful our telescopes become. They exist in a region of the universe permanently cut off from observation. But within the observable universe, redshift acts as a precise clock. There is debate among physicists about whether redshift is purely due to expansion or whether light inherently loses energy over cosmic distances. A few fringe theories propose that photons decay slightly over billions of years, shifting to longer wavelengths through a mechanism unrelated to expansion. Mainstream science rejects this idea because observations consistently match expansion models. But the debate lingers in corners of cosmology, a reminder that even well-established physics contains mysteries we have not fully explored. What James Webb does with redshift is remarkable. The telescope captures light from a distant galaxy. Its spectrograph splits that light into individual wavelengths, creating a spectrum. Within that spectrum appear bright or dark lines at specific wavelengths, signatures of hydrogen, oxygen, carbon, and other elements. These elements always emit or absorb light at the same wavelengths no matter where they are in the universe. Hydrogen produces a specific line at 121 nanometers. always. This is a law of physics. But when astronomers look at the spectrum from a distant galaxy, that hydrogen line does not appear at 121 nanometers. It appears shifted to a longer wavelength. Maybe it shows up at 600 nanometers. Maybe 1200. The amount of shift tells them exactly how far the light has travelled and how long ago it left. This turns every observation into archaeology. James Webb is not just seeing distant galaxies, it is excavating time itself. Each spectrum is a fossil, each photon a messenger from an era when the universe was young, hot, dense, and unrecognizable compared to the cosmos we inhabit now. The farthest light ever captured by James Webb left its source 280 million years after the Big Bang. The universe was 2% of its current age. If you compressed cosmic history into a single year, this galaxy formed on January 7th. We are looking at cosmic infancy. We are witnessing creation still unfolding. And every photon that reaches the telescope has been stretched, transformed, encoded with information about expansion, distance, and time. Light remembers everything. It carries within it the story of how far it has travelled and when it began. James Webb reads these stories, one spectrum at a time, one galaxy at a time, building a history of the universe written in wavelengths of invisible light. There is a galaxy named MUMS Z14. Astronomers confirmed its distance in early 2025. When they measured its redshift, the number came back as 14.44. That single measurement represents the farthest confirmed object human beings have ever observed. The light we see from this galaxy left when the universe was only 280 million years old. 2% of cosmic history had passed. Everything was still forming, still raw, still impossibly young. Think about that ratio for a moment. The universe today is 13.8 billion years old. MUMS Z14 existed when barely 300 million years had elapsed. If you compressed the entire history of the cosmos into one calendar year, this galaxy assembled itself by January 7th. We are living in late December of that cosmic year. We are looking backward across nearly the entire story. The discovery happened through careful hunting. James Webb does not randomly photograph the sky hoping to find distant galaxies. Astronomers search through existing images looking for candidates. They identify objects that appear unusually red, suggesting extreme redshift. When they spotted the faint signal of MUMS Z14, they turned the telescope back toward it in April 2025 for confirmation. The instrument they used is called a spectrograph. It splits light into its component wavelengths, revealing the fingerprints of elements inside the galaxy. The spectrum came back clear. Hydrogen lines appeared shifted to wavelengths far beyond where they should be. The measurement was precise. Not a guess, not an estimate. Real data proving this galaxy existed at the edge of what we can observe. What shocks scientists about MUMS 1Z14 is that it is not a tiny faint speck struggling to survive. The galaxy is bright. It is actively forming stars in a burst of rapid creation. When astronomers analysed the spectrum, they found nitrogen levels similar to ancient star clusters in our own Milky Way. Nitrogen is a heavy element. It does not exist naturally after the Big Bang. It must be created inside stars through nuclear fusion. When massive stars explode as supernovas, they scatter nitrogen into space. The next generation of stars incorporates this nitrogen into their composition. The presence of nitrogen means MUMS Z14 already went through at least one or two generations of stars. Stars formed, lived their lives, exploded, enriched the surrounding gas, and allowed new stars to form from that enriched material. All of this happened in less than 300 million years. For comparison, Earth has existed for 4.5 billion years. Dinosaurs walked this planet for 165 million years. MUMS Z14 completed multiple cycles of star birth and death in less time than dinosaurs roamed. The timeline is compressed impossibly tight. According to older models of galaxy formation, this should not be possible. Galaxies were supposed to grow slowly over hundreds of millions of years. Dark matter halos form first, creating gravitational wells. Gas falls into those wells gradually. Stars ignite one cluster at a time. The galaxy builds mass carefully, adding structure over vast periods. MUM's Z14 shows us they did not grow this way. Not in the early universe. They appeared fast, shining intensely, building themselves at breakneck speed. Here is something scientists debate quietly. MUM's Z14 beat the previous distance record by only 10 million years. That sounds small. A rounding error on cosmic timescales. But in the infant universe, everything changed incredibly fast. 10 million years represents a significant fraction of available time when the universe itself is only 300 million years old. Some researchers wonder if there is a natural barrier around this distance, a point beyond which galaxies simply could not form because conditions were too chaotic, too hot, or too unstable. Others believe MUM's Z14 is nowhere near the limit. They expect galaxies even farther back, hiding just beyond our current detection threshold. The Nancy Grace Roman Space Telescope will launch in 2027. It is designed to scan massive portions of sky much faster than James Webb can. Roman will survey wide areas, identifying thousands of candidate galaxies from the earliest cosmic eras. Many of these will likely push past MUM's Z14, revealing objects that formed even earlier. Each new discovery moves the boundary closer to the Big Bang itself. And every time we push that boundary, we find something that breaks expectations. Galaxies forming too fast, structures appearing too early, brightness levels exceeding predictions. The universe does not follow the slow, patient progression our models describe. It moves violently when conditions allow. Forces we do not fully understand drove galaxy formation in those early years with intensity we no longer see today. What did the universe look like when MUM's Z14 assembled itself? Space was much smaller then. Everything was closer together. The average temperature was higher because matter was compressed into less volume. Radiation from the Big Bang still filled the cosmos, though it had cooled significantly from its initial fireball state. Dark matter halos were forming everywhere, acting as invisible scaffolding where regular matter could gather and collapse. The gas itself was almost pure hydrogen and helium. These are the only elements the Big Bang produced in significant quantities. No oxygen yet, no carbon, no nitrogen, none of the elements that make up planets or life or your body. Those elements had to be forged inside the first stars. When massive stars exploded, they scattered these heavier elements into space. The next generation incorporated them. This process is called stellar nucleosynthesis, and it takes time. Multiple cycles. Multiple explosions. MUM's Z14 had already completed these cycles. In under 300 million years. There is a strange and unsettling thought some cosmologists entertain. If galaxies like MUM's Z14 formed so early and so quickly, what does that say about the possibility of life appearing early as well? Stars in these ancient galaxies created heavy elements fast. Planets could have formed around second-generation stars within the first billion years after the Big Bang. If planets existed, could life have emerged? Could civilizations have risen and fallen billions of years before Earth even formed? The idea is speculative, bordering on science fiction. But the speed at which MUM's Z14 built itself makes such speculation less absurd than it once seemed. What we know for certain is this. Light left MUM's Z14 when the cosmos was in its infancy. That light travelled through expanding space for over 13 billion years. It stretched from visible wavelengths into deep infrared. It crossed distances so vast that the numbers become meaningless. And it arrived at James Webb's mirrors carrying proof that galaxies blazed into existence faster and earlier than we ever imagined. MUM's Z14 is probably not the limit. Something farther awaits discovery. Something older. Something closer to the moment when darkness ended and light began. We stand at the edge of that revelation, photons away from witnessing the very dawn of cosmic structure. Close your eyes and picture absolute nothingness. No light, no stars, no galaxies glowing in the distance. Just hydrogen and helium gas floating in darkness, cooling as space expands. This is what the universe looked like for hundreds of millions of years after the Big Bang. Scientists call this period the Cosmic Dark Ages. It lasted longer than you might think, longer than seems possible for a universe destined to fill with light. For the first few 100 million years, nothing burned. Nothing shone. The Big Bang's initial fireball had faded. The cosmic microwave background radiation, once blinding and hot, had cooled and stretched into wavelengths too long to see. The universe was truly dark. If you could have existed then, floating in that primordial void, you would have seen nothing in any direction, no matter how long you waited, no matter how far you looked. But gravity never sleeps. Even in total darkness, invisible forces were working. Dark matter had already formed vast halos, regions where its gravity concentrated. These halos acted like gravitational wells, pulling in the hydrogen and helium gas floating through space. Gas clouds drifted toward these wells, slowly accumulating. Density increased, pressure built. Temperatures began to rise in the densest cores. Somewhere in the darkness, a threshold was crossed. A cloud of gas collapsed so completely that its core reached 10 million degrees. At this temperature, hydrogen atoms begin to fuse. They combine into helium, releasing tremendous energy. A star ignites. Light floods outward for the first time since the Big Bang's glow faded. This moment ended the Cosmic Dark Ages. This moment began the Cosmic Dawn. We do not know exactly when the first star ignited. The best estimates place it somewhere between 150 and 300 million years after the Big Bang. That is a wide range. 150 million years of uncertainty. Some models suggest the first stars appeared quickly, blazing into existence as soon as conditions allowed. Others propose a slower process, with many false starts before stable star formation began. The debate remains open because we have not yet observed a population 3 star, the term for these first-generation objects. Population 3 stars would have been different from any star you see in the night sky today. Modern stars form from gas enriched with heavy elements: carbon, oxygen, nitrogen, iron. These elements, called metals in astronomy, help gas clouds cool and fragment into smaller pieces. This allows stars of various sizes to form, from tiny red dwarfs to massive blue giants. But the first stars had no metals. They formed from pure hydrogen and helium. Without metals to facilitate cooling, the gas could not fragment efficiently. Instead of forming many small stars, the clouds collapsed into fewer, much more massive objects. The first stars likely weighed between 50 and several hundred times what our Sun weighs. Some theories propose even larger objects, supermassive stars weighing thousands of solar masses, though this remains speculative. These massive first stars burned incredibly hot and bright. They poured out ultraviolet radiation at rates far exceeding anything modern stars produce. This ultraviolet light began to change the universe. When a photon of ultraviolet light strikes a hydrogen atom, it can knock the electron free. The atom becomes ionized. It transforms from neutral hydrogen into a proton and a free electron floating separately. Around each first star, a bubble of ionized gas formed. The star's radiation pushed outward, ionizing more and more hydrogen. The bubble grew. At first these bubbles were isolated. Stars formed in scattered locations across the universe, each creating its own sphere of ionization. The regions between bubbles remained dark and neutral. But over time, more stars formed, more bubbles appeared. Eventually, the bubbles began to touch. They merged into larger ionized regions. This process is called reionization. It transformed the entire universe from a neutral gas-filled void into an ionized plasma. Reionization did not happen instantly. It took hundreds of millions of years to complete. Early on, only small patches of space were ionized. By about 400 million years after the Big Bang, most of the universe had been reionized. James Webb is observing galaxies from this exact era. The cosmic dawn, the transition from darkness to light. Galaxies like Mum's Z14 formed during this period. They contain the descendants of the first stars. Some may even harbour a few population 3 stars still burning, though most of those ancient giants died long ago. What we see in these early galaxies is the aftermath, the evidence that light won. That darkness gave way. Here is something strange that astronomers have noticed. The early galaxies James Webb found are contributing more ultraviolet light than models predicted. This excess light suggests reionization may have completed earlier than previous estimates indicated. If the galaxies were brighter, they produced more ionizing photons, transforming the universe from neutral to ionized faster. Some researchers propose this means we are missing a population of very bright objects in the early universe. Perhaps supermassive stars did exist and contributed significantly to reionization. Perhaps early black holes, feeding rapidly, added their radiation to the process. The cosmic dawn also marked the creation of the first heavy elements. When massive stars exhaust their hydrogen fuel, they begin fusing heavier elements in their cores. Helium fuses into carbon, carbon fuses into oxygen. The process continues up the periodic table, creating nitrogen, silicon, sulfur, iron. When the star finally runs out of fuel, it explodes as a supernova. This explosion scatters the newly created elements into space. The first supernovas poisoned the universe with metals. Poisoned is the wrong word. Enriched. They enriched the pristine hydrogen and helium with the building blocks of complexity. The next generation of stars formed from this enriched gas. They incorporated carbon and oxygen into their structure. When planets formed around these stars, they contained metals. Rocky worlds became possible, chemistry became complex, and eventually, billions of years later, life became possible. Without the cosmic dawn, none of this happens. Without the first stars igniting, the universe remains a dark ocean of hydrogen and helium forever. No planets, no chemistry, no biology, no consciousness. The moment the first star began to shine was the moment the universe became capable of creating observers, creating you. James Webb cannot see the first stars directly. They died over 13 billion years ago. What the telescope sees is their legacy. Galaxies filled with second and third generation stars, gas clouds enriched with metals those first stars created, the ionized state of intergalactic space their radiation produced. The cosmic dawn itself is over, but its light still reaches us, redshifted and stretched, carrying evidence of the moment darkness learned to glow. Imagine that transition, from perfect blackness to the first pinpricks of light, from silence to the roar of fusion, from simplicity to the complexity that would eventually build galaxies, planets, oceans, forests, mines, all of it beginning with a single collapsing cloud of gas that crossed a threshold and ignited. The universe went from night to day in a cosmological instant, and we are living in the endless afternoon that followed, looking back through telescopes at the dawn we missed, witnessing the birth of light itself 13 billion years too late. Galaxies were supposed to grow slowly, carefully. Over billions of years, gas would accumulate. Stars would form gradually. Mass would build up through patient processes. The simulations told us this. The models predicted it. The mathematics demanded it. James Webb looked into the early universe and found the models were wrong. The telescope discovered massive galaxies existing when the universe was only 300 to 500 million years old. Not small dwarf galaxies taking their first breaths, not tiny clusters of stars struggling to survive. Massive, bright, fully formed systems containing billions of times the mass of our Sun. Galaxies that should not exist yet. Galaxies that had no time to build themselves. One example sits at redshift 11, The numbers tell a story. Redshift 11 means the universe was only 400 million years old when this galaxy shone. Astronomers measured its mass. 10 billion times heavier than our Sun. 10 billion stellar masses assembled in less than 400 million years. For comparison, the Milky Way has existed for over 13 billion years. It had time to build itself through countless cycles of star formation, mergers, and gradual accumulation. This early galaxy accomplished similar mass in a fraction of the time. The problem is the timeline. Building a galaxy requires steps. Dark matter halos must form first, creating gravitational wells. Gas must fall into these wells, accumulating over millions of years. The gas must cool and collapse into dense clouds. Those clouds must fragment and form stars. The stars must live, die, and enrich the gas with heavier elements. New generations of stars must form from this enriched material. Each step requires time. Yet these early galaxies completed all the steps in under 500 million years. The universe moved faster than physics seemed to allow. Before James Webb, astronomers thought they understood galaxy formation reasonably well. The Hubble Space Telescope found galaxies in the early universe. Their numbers and brightness matched predictions closely enough. Simulations run on supercomputers produced virtual universes that looked similar to observations. The models worked. Scientists felt confident. Then James Webb began operations and revealed 10 times more bright galaxies in the early universe than models predicted. 10 times. Not a small discrepancy. Not something explainable by minor adjustments. A fundamental mismatch between theory and reality. What makes early galaxies so bright? Several theories compete for attention. The first involves star formation efficiency. Modern galaxies convert only a small fraction of their gas into stars. Most gas gets blown away by stellar winds, heated by radiation, or remains unconverted. Perhaps the first galaxies were more efficient. Perhaps they turned a much higher percentage of their gas into stars. If every collapsing cloud successfully formed stars instead of being disrupted, the galaxy would produce far more stellar mass in less time. More stars mean more light. The galaxy shines brighter. But why would early galaxies be more efficient? One possibility is that feedback mechanisms were weaker. In modern galaxies, when massive stars explode as supernovas, they blast gas out of the galaxy entirely. This feedback slows down future star formation by removing the raw material needed to make new stars. Perhaps in the early universe, galaxies were denser and gravity was stronger. The exploding stars could not eject gas as easily. The gas stayed inside the galaxy, continuing to form stars at high rates. A second theory involves the types of stars being formed. Not all stars shine equally. A star 100 times heavier than our Sun can be 1 million times brighter. If early galaxies produced a higher proportion of massive stars, their total light output would increase dramatically. The stellar mass function, which describes how many stars of each size form, might have been different in the early universe. More massive stars, fewer small stars. The result would be galaxies that shine far brighter for their total mass. Some scientists go further and suggest supermassive stars. These hypothetical objects would weigh hundreds or even thousands of times what our Sun weighs. They would burn with the intensity of entire modern galaxies. Each supermassive star would live only a few million years before exploding catastrophically. But during that brief life, it would dominate the light output of its host galaxy. If even a small fraction of early stars were supermassive, they would explain the excess brightness James Webb observes. The challenge is that supermassive stars remain purely theoretical. No telescope has ever confirmed one. We have equations suggesting they could form under certain conditions. We have models showing what their spectra might look like. But we have no direct evidence they ever existed. They remain an elegant solution to a problem, waiting for proof. A third possibility centers on black holes. Active supermassive black holes emit enormous amounts of light as they consume matter. If early galaxies contained more actively feeding black holes than expected, their combined radiation could boost the galaxy's total brightness. James Webb has found numerous early galaxies with signs of black hole activity, but not all bright early galaxies show these signs. Black holes alone cannot explain the entire brightness excess. Dark matter adds another layer of mystery. The simulations use specific values for dark matter density and behavior. If those values are slightly wrong, the predictions change. Perhaps dark matter clumped together more efficiently in the early universe. Perhaps the initial density fluctuations from the Big Bang were stronger than we calculated. Either change would allow galaxies to form faster and grow larger in less time. Mergers might contribute as well. If small galaxies formed very early and immediately began colliding and merging, they could combine their masses quickly. Each merger adds stars, gas, and dark matter. A series of rapid mergers could build a massive galaxy in a compressed time frame. However, mergers alone probably cannot explain the most extreme cases. There simply was not enough time for multiple large mergers to occur in the first few 100 million years. Here is what unsettles astronomers the most. These massive early galaxies are not just bright. They are also mature. Their spectra show signs of older stellar populations, stars that have been shining for tens or hundreds of millions of years already. Some galaxies even contain dust, which forms from supernova debris. Dust takes time to accumulate. Its presence means the galaxy already cycled through multiple generations of stars. Birth, life, death, enrichment, rebirth. All of it compressed into a timeline that seems impossibly short. The universe in its infancy was not a quiet nursery. It was a forge. Galaxies appeared fast, burned bright, and built themselves with an intensity we no longer see today. Whatever forces drove galaxy formation in those early years operated at a level our current models cannot reproduce. Every massive early galaxy James Webb finds is a challenge. A question mark etched into cosmic history. How did you form so fast? What rules were you following that we do not understand? The answers are still emerging, the data still accumulating, but one thing is clear. The universe does not follow the slow, patient timeline we imagined. When conditions allow, it moves with shocking speed. A black hole is born when a massive star dies. The star exhausts its fuel. Its core collapses in a fraction of a second. If the star was heavy enough, 20 times the mass of our Sun or more, the collapse does not stop. Gravity crushes the core past any possible resistance. It becomes a point of infinite density. A black hole. This newborn black hole weighs perhaps 50 times what our Sun weighs. 50 solar masses of compressed matter surrounded by an event horizon from which nothing can escape. This is how stellar mass black holes form. They are small by cosmic standards, common throughout the universe, unremarkable in the grand scheme. But at the centres of galaxies sit monsters. Supermassive black holes weighing millions or billions of times our Sun's mass. The one at the heart of our Milky Way weighs about 4 million solar masses. The largest known black holes exceed 10 billion. These are not objects born from a single dying star. They are empires of gravity that took eons to build. Or so we thought. James Webb found a black hole in a galaxy called Canucks-LRDZ86. The name is a catalogue designation, meaningless except to the astronomers who study it. What matters is when this galaxy existed. The light we see left when the universe was 570 million years old, barely 500 million years after the Big Bang. And at the centre of this infant galaxy sits a supermassive black hole weighing millions of times what our Sun weighs. The math does not work. You cannot grow a black hole from 50 solar masses to millions in only 500 million years through normal feeding. A black hole consumes matter by pulling it inward with gravity. Gas, dust and stars fall toward the event horizon. As this matter spirals inward, friction heats it to millions of degrees. It glows brilliantly before disappearing forever. This process is called accretion. It is how black holes eat, how they grow. But there is a speed limit. When matter falls toward a black hole and heats up, it emits intense radiation, light, X-rays, ultraviolet energy streaming outward. This radiation exerts pressure. It pushes against the infalling matter. If too much matter tries to fall in too fast, the radiation becomes so intense it blows the matter away. The black hole chokes on its own light. It cannot eat faster than this limit. Physicists call it the Eddington limit, named after Arthur Eddington, who calculated it a century ago. At the Eddington limit, a black hole weighing 1 million solar masses can grow by about 1% every million years. Steady feeding at maximum rate for 700 million years, starting from a 50 solar mass seed, would produce a black hole of only moderate size, not millions of solar masses. Certainly not the billions James Webb has observed in some early galaxies. The black hole in Cannu CSLRD Z86 should not exist at its observed mass, not with only 500 million years to grow, not if physics worked the way our models describe, yet spectroscopy confirmed it. The data is real. The black hole is there, which means something about our understanding is incomplete. Two main theories attempt to explain these impossible monsters. The first suggests that black holes did not start small. Instead of forming from dying stars, they formed directly from massive gas clouds. Under very specific conditions, a cloud containing tens of thousands of solar masses of gas could collapse straight into a black hole without forming a star first. This would create what scientists call a heavy seed black hole. Instead of starting at 50 solar masses, it begins at 10,000 or even 100,000. That head start makes reaching millions of solar masses far more achievable in limited time. The conditions required for direct collapse are rare. The gas must be almost pure hydrogen and helium, with no heavy elements to help it cool. It must also be bathed in strong ultraviolet radiation that prevents hydrogen molecules from forming. Without molecules, the gas cannot cool efficiently. It stays hot. And hot gas cannot fragment into stars. Instead, the entire cloud collapses into a single massive object that immediately becomes a black hole. Some astronomers think these conditions were common during the cosmic dawn. The first generation of stars produced intense ultraviolet radiation. Nearby gas clouds, heated by this radiation, might have collapsed directly into heavy seed black holes. If this happened frequently, the early universe would have been littered with large black holes, ready to grow even larger. The second theory involves supermassive stars. If stars weighing hundreds or thousands of times our sun's mass formed in the early universe, they would live only a few million years before collapsing. When they died, they would leave behind black holes already weighing thousands of solar masses. Again, a significant head start. Both theories share a problem. We have no direct evidence for either. Direct collapse black holes and supermassive stars are theoretical, predicted by physics but never observed. They remain elegant solutions waiting for proof. Then James Webb found something extraordinary. A black hole named LID 568. This black hole sits in a galaxy visible as it existed 1.5 billion years after the Big Bang. The Chandra X-ray Observatory and James Webb both observed it. The data revealed something that should be impossible. LID 568 is feeding at over 40 times the Eddington limit. 40 times faster than physics says a black hole can consume matter. The black hole is gorging itself. Gas swirls around it at incredible speeds. The gas is highly ionized, meaning radiation has stripped electrons from atoms. X-rays scream into space. The energy output is staggering. If this feeding rate continued for just a few million years, the black hole would double its mass. This is not slow, patient growth. This is explosive expansion. Astronomers call this super Eddington accretion. It happens when matter falls in from all directions simultaneously, overwhelming the radiation pressure through sheer volume. Imagine trying to stop a flood with a fan. The water wins. If enough gas collapses onto a black hole at once, the outward radiation cannot push it all away fast enough. The black hole devours everything. These feeding frenzies are likely rare and short-lived. A black hole cannot sustain super Eddington accretion for millions of years. The nearby gas supply runs out, but during the brief window when it happens, enormous mass gets added quickly. A few episodes like this scattered across cosmic history could explain how black holes reached millions or billions of solar masses within the first billion years. LID 568 is the first confirmed observation of super Eddington feeding. Before this, it was theoretical, a possibility suggested by equations but never witnessed. Now we know it happens. The question shifts from whether it is possible to how often it occurred. Some researchers propose a dark possibility. Perhaps many black holes in the early universe fed this way. Perhaps the chaotic conditions of the infant cosmos made super Eddington accretion common rather than rare. Gas was denser back then. Galaxies collided more frequently. Each collision could trigger a burst of rapid feeding. Over time, through multiple episodes, black holes grew far faster than steady accretion would allow. The universe in its youth was wilder than we imagined. Black holes did not follow the limits we calculated. Under the right conditions, they broke the rules entirely, and the evidence is written in the spectra of ancient galaxies, where monsters lurk impossibly early, too massive for their age, too hungry for the physics we thought governed them. James Webb started finding them almost immediately. Tiny red smudges scattered across deep field images. At first glance, astronomers thought they were ordinary distant galaxies. Faint objects made red by extreme redshift. Nothing unusual, nothing to worry about. Then the spectroscopy came back. These objects are not ordinary, not even close. Scientists call them little red dots. The name sounds casual, almost playful, but what these objects represent is anything but. Over 100 have been identified so far. They share common traits that make them deeply strange. First, they are small, much smaller than typical galaxies from the same era. Second, they are extremely red because their light has been stretched by cosmic expansion across billions of years. Third, they are bright, far too bright for their size. And fourth, they contain either impossibly dense star clusters or massive black holes that should not fit inside them. Here is what makes little red dots bizarre. When astronomers calculate the mass of stars needed to produce their brightness, the numbers become absurd. The stars would need to be packed so tightly that they would constantly collide and merge, stars crashing into each other continuously, stellar cores slamming together, releasing energy, destroying themselves. This does not happen in any galaxy we see today. The density required is beyond anything physics allows for stable stellar systems. Alternatively, if a supermassive black hole is producing the light instead of stars, then the black hole is too big for its galaxy. In modern galaxies, the central black hole weighs about 0.1% of the galaxy's total stellar mass. A 4 million solar mass black hole sits at the center of the Milky Way, which contains about 60 billion solar masses of stars. The ratio is tiny. Black holes are minor players in the mass budget of their galaxies. Little red dots invert this relationship completely. In some of these objects, the black hole weighs as much as all the stars combined. The black hole dominates. The galaxy is almost an afterthought. The central monster outweighs everything else. Both explanations break existing models. We thought galaxies and their central black holes grew together, maintaining a balanced ratio throughout cosmic history. The galaxy forms first. Stars accumulate. The black hole grows slowly at the center, feeding on gas that drifts inward. Over billions of years they reach equilibrium, a dance of gravity where neither partner vastly outweighs the other. Little red dots suggest this dance sometimes fails entirely. The black hole got huge first. The galaxy never caught up. Another mystery is their abundance. Before James Webb, astronomers expected to find perhaps a handful of unusual objects in the early universe, rare exceptions to normal galaxy formation. Instead, there are hundreds. Little red dots are not rare oddities. They are common, Whatever process created them was not a fluke. It was a standard part of how the early universe worked. This discovery challenges the fundamental picture of galaxy evolution. If black holes routinely dominated their host galaxies in the first billion years after the Big Bang, then our understanding of how galaxies assembled is incomplete. We need new models, new equations, new explanations for how gravity, gas, and dark matter interacted during those chaotic early times. Some scientists think little red dots are transition objects. We might be catching galaxies in the middle of a growth spurt. The black hole is feeding rapidly right now, gorging on gas, shining with enormous energy. Meanwhile, the surrounding galaxy has not had time to catch up. It is still forming stars, still building mass. Over millions of years, the galaxy might grow larger, the star count might increase. Eventually, the ratio between black hole and galaxy might normalize. If this theory is correct, little red dots represent a phase, a temporary state all galaxies pass through before maturing. Every massive galaxy today might have been a little red dot billions of years ago. A brief period when the black hole dominated before the galaxy bulked up around it. Others propose something more radical. Perhaps some galaxies form black holes first and build stars around them later. The black hole is not a product of galaxy evolution. It is the seed. Gravity from the black hole attracts gas. The gas accumulates and forms stars. The galaxy grows outward from its central monster. This reverses the conventional timeline completely. There is a fringe hypothesis worth mentioning. A few researchers suggest that little red dots might not be galaxies at all. They could be something else entirely. Dense clusters of primordial black holes left over from the very early universe. Objects that formed in the first moments after the Big Bang through entirely different physics. This idea remains highly speculative. Most astronomers reject it. But the strangeness of little red dots keeps the door open for unusual explanations. What we know for certain is that little red dots are not going away. Every new James Webb observation finds more of them. They appear at multiple distances. They existed throughout the first billion years of cosmic history. They were everywhere during the cosmic dawn, scattered across the sky like red embers from a dying fire. The most unsettling part is what they reveal about our models. We built equations to describe how galaxies form. We ran computer simulations to test those equations. The simulations predicted slow, steady growth. They predicted galaxies forming stars over billions of years. They predicted black holes staying small relative to their host galaxies. Little red dots break all three predictions simultaneously. The universe did not wait patiently in its youth. It was not orderly or careful. It was chaotic and fast and violent. Forces we do not fully understand drove structures to form at rates our physics cannot explain. Little red dots are proof, evidence written in infrared light that the early cosmos played by different rules. Each little red dot James Webb finds adds to the puzzle. Each observation refines our understanding while raising new questions. What allowed black holes to grow so dominant? Why did some galaxies form stars so densely? How did these compact objects survive without destroying themselves? The answers remain incomplete. The data keeps arriving. Every spectrum reveals new details. Every image shows new candidates waiting for analysis. James Webb has opened a window into a universe far stranger than we predicted. And looking through that window, we see little red dots everywhere, scattered across the deep fields, glowing with impossible brightness, challenging everything we thought we knew about how galaxies come to be. They are small. They are red. They are cosmic mysteries wrapped in faint infrared light. And they are rewriting the story of the universe one observation at a time. A black hole is running away from home, not metaphorically, not poetically, actually running, moving through space at 2 million miles per hour. That is 3,000 times the speed of sound. Fast enough to cross the distance between Earth and the Moon in less than 2 minutes. And this is not a small black hole. It weighs 10 million times what our Sun weighs. a supermassive giant fleeing through the cosmos, dragging a trail of newborn stars behind it like a scar across the sky. James Webb confirmed this discovery in 2025. Astronomers are calling it the first verified runaway supermassive black hole. Nothing like it has ever been observed before. The object sits in a system called the cosmic owl, which is actually multiple galaxies in the process of merging. When galaxies collide, their central black holes eventually sink toward the center of the combined system. Usually they merge. Sometimes gravity plays a cruel trick instead. There are two ways to eject a black hole this massive. The first involves gravitational waves. When two supermassive black holes spiral together and merge, they release ripples in spacetime. These ripples carry momentum. If the gravitational waves are emitted unevenly, they can give the resulting black hole a powerful kick. Like recoil from a gun. The merged black hole gets shoved in one direction at tremendous speed. Velocities can reach thousands of miles per second. More than enough to escape the galaxy entirely. The second method requires three black holes. Imagine a galaxy that already has a pair of black holes orbiting each other at its center. A third black hole enters the system during a merger with another galaxy. Three massive objects interacting gravitationally is unstable. The math becomes chaotic. One of the three always loses. It gets flung outward while the other two remain bound together. This is called the three-body problem. It has no stable solution. One object always gets ejected. Something kicked this black hole out of its home galaxy with enough force to send it racing through intergalactic space forever. James Webb detected the runaway by observing a bow shock in front of it. As the black hole plows through thin gas at enormous speed, it compresses the gas ahead of it. This compression creates a shock wave, like a boat pushing water aside as it moves. The shocked gas heats up and glows. The telescope also detected something behind the black hole. A long trail stretching 200,000 light-years. A ribbon of newborn stars forming in the wake of the fleeing monster. This is unprecedented. Stars forming because a black hole passed by. When the black hole moves through intergalactic gas, its gravity compresses the material it passes. This compression triggers collapse. Gas clouds that would have drifted quietly for billions of years suddenly condense and ignite as stars. The black hole creates a line of stellar birth along its entire path. Young stars glow in ultraviolet and visible light. Their brightness reveals the trail, a cosmic highway marked by creation instead of destruction. At 2 million miles per hour, this black hole will never stop. It will continue moving through space until the end of time. It will leave its galaxy system entirely. It will wander through the voids between galaxies as a rogue object, invisible because it no longer has matter to feed on. A supermassive black hole drifting through emptiness, forever homeless. How common are runaway black holes? Before this discovery, we had no confirmed examples. Computer simulations predicted they should exist. Galaxy mergers are violent events. Black hole interactions are chaotic. Occasionally physics should eject one. But finding them is difficult. A black hole that is not actively feeding produces no light. It becomes invisible. Only during the ejection phase, when it is still interacting with gas and leaving a visible trail, can we detect it. This raises an uncomfortable question. How many rogue black holes drift through the universe right now, completely undetected? Thousands? Millions? We cannot know. They could be passing through our own galaxy without our awareness. Invisible monsters wandering the dark, their presence betrayed by nothing. While one black hole runs, two others are about to collide. James Webb found a pair of supermassive black holes spiraling toward each other in a galaxy system called ZS7. This system existed 740 million years after the Big Bang. Both black holes weigh millions of times what our Sun weighs. They orbit each other at a separation of only a few thousand light-years. They are moving closer, spiraling inward. In cosmic terms, their collision is inevitable. When two supermassive black holes merge, the event shakes spacetime itself. Gravitational waves ripple outward from the collision. More energy gets released in that single moment than all the stars in the visible universe produce combined. The waves spread across billions of light years, stretching and compressing space as they pass. If you could feel them, you would sense your own body briefly expanding and contracting by amounts smaller than an atom. We cannot detect the gravitational waves from ZS7 with current technology. The waves have been travelling for over 13 billion years. They have stretched and weakened, but future observatories will hear them. The Laser Interferometer Space Antenna, scheduled to launch in the 2030s, is designed specifically for this purpose. It will detect gravitational waves from supermassive black hole mergers throughout the universe. Events like ZS7 will become routine observations. This discovery tells us something important. Black hole mergers were common in the early universe. We thought they might be rare. Unusual events that happened occasionally during galaxy collisions. Instead, James Webb shows us merging black holes at extreme distances. Multiple systems. Multiple examples. If mergers were frequent then, they contributed significantly to black hole growth. 2 million solar mass black holes combining produce a 4 million solar mass black hole instantly. No waiting, no slow feeding, merger is a shortcut. The merger also reveals how galaxies themselves evolve. ZS7 formed from two galaxies colliding. As they combined, their black holes sank toward the center of the new system through a process called dynamical friction. They interacted with stars and gas, losing energy, spiraling inward. Eventually they formed a binary pair. Now they approach the final stage, the merger that will complete their union. This same process will happen to our own galaxy. The Milky Way is on a collision course with the Andromeda Galaxy. In about 4 billion years the two will merge. Their central black holes will eventually combine. Gravitational waves will ripple outward. Future observers, if any exist, will witness the event from whatever remains of our solar system. Black holes on the run. Black holes spiraling toward collision. The universe is dynamic. Objects we thought were stationary are actually in motion. Events we thought took billions of years are happening right now, frozen in time by the distance their light must travel. James Webb captures these moments. A runaway monster trailing stars. A doomed pair approaching annihilation. The cosmos is far more active than our intuition suggests. The universe is bigger than you think. Much bigger. The number most people know is wrong. You have probably heard that the universe is about 14 billion years old. This is correct. The Big Bang happened 13.8 billion years ago. Light has been travelling through space ever since. If you imagine the universe as a sphere with Earth at the centre, you might think it extends 14 billion light-years in every direction. A diameter of 28 billion light-years. That seems logical. Light travels at a fixed speed. The universe has a fixed age. The math should be simple. But the math is not simple. The universe does not work that way. The observable universe spans 93 billion light-years across. Not 14 billion, not 28. 93. A diameter more than 3 times larger than our intuition suggests. This seems impossible. How can the universe be bigger than the distance light could travel since the beginning of time? The answer is expansion. Space itself has been growing since the Big Bang, not just the objects in space moving apart, the actual fabric of existence stretching larger every moment. When a photon of light leaves a distant galaxy and travels toward us, the space it travels through expands while the photon is moving. The finish line keeps receding. The photon eventually arrives, but the galaxy that emitted it has moved much farther away during the journey. Consider a galaxy whose light left 13 billion years ago. That photon has been travelling toward us ever since, but the space between us and that galaxy has been expanding the entire time. Today that galaxy sits not 13 billion light-years away, it sits over 40 billion light-years away. The expansion of space carried it outward even as its ancient light was falling toward us. This is why the observable universe has a radius of about 46 billion light-years. Multiply by 2 for diameter. 93 billion light-years across. A sphere containing everything we can theoretically see. Everything whose light has had time to reach us since the beginning. Beyond this sphere lies more universe. We cannot see it. Its light has not arrived yet. Some of it will never arrive because space is expanding faster than light can travel. But it exists. The universe does not end at the boundary of what we can observe. It continues outward, possibly forever, possibly looping back on itself in shapes we cannot imagine. James Webb operates within this observable sphere. It captures light from the most distant objects whose photons have reached Earth. The farthest confirmed galaxy, MUM Z14, sits at a comoving distance of over 33 billion light-years. Comoving distance accounts for expansion. It tells us where the galaxy is now, not where it was when the light left. When that photon began its journey, the galaxy was much closer. Expansion pushed it outward while the light travelled. The Cosmos Web Survey revealed the scale in staggering detail. James Webb spent over 200 hours observing one patch of sky, covering an area about 3 times the size of the full moon. Within that tiny region, the telescope found nearly 800,000 galaxies, each one a complete system of billions of stars. Each one existing at different distances, meaning different times in cosmic history. 800,000 galaxies in a patch of sky you could cover with 3 fingers held at arm's length. The entire celestial sphere contains over 40,000 square degrees. If every patch holds similar density, the total number of galaxies in the observable universe exceeds 2 trillion. 2 million million. A number so large it loses all meaning. Each of those galaxies contains billions of stars. Each star potentially hosts planets. The number of worlds in the observable universe becomes incomprehensible. Even if only a tiny fraction of planets can support life, the total number of potentially habitable worlds is staggering. We are not unique in terms of location. We occupy one planet orbiting one star in one galaxy among 2 trillion. Here is something even more unsettling. James Webb has found structures that formed too early and too large. Galaxy clusters and groups that should have taken longer to assemble. The cosmic web, with its filaments and voids, was already taking shape when the universe was just a few billion years old. Gravity pulled galaxies together faster than models predicted. One survey found a structure stretching over 3 billion light-years across. A wall of galaxies forming a boundary between cosmic voids. This is among the largest known structures in the universe. A filament of matter so vast that light takes billions of years to cross it, and it existed earlier than our simulations said it should. Dark matter drives this clustering. It outweighs visible matter by about 5 to 1. Dark matter halos formed first after the Big Bang, creating gravitational scaffolding for regular matter to accumulate. The halos pulled hydrogen and helium inward, beginning the process of galaxy formation. Without dark matter, galaxies would not exist. Stars would not exist. Planets would not exist. You would not exist. Yet we do not know what dark matter is. We detect it only through gravity. It does not emit light. It does not absorb light. It passes through ordinary matter without interacting. Billions of dark matter particles might be streaming through your body right now without touching a single atom. We know it is there because galaxies rotate too fast for their visible mass. Something invisible holds them together. Something we cannot see, cannot touch, and cannot explain. Some physicists propose that dark matter consists of undiscovered particles. Others suggest modifications to gravity itself. A few fringe theories question whether dark matter exists at all, proposing instead that our understanding of physics is incomplete on cosmic scales. The debate remains open, one of the deepest mysteries in modern science. There is another unsettling thought. The universe is expanding faster now than it was in the past. Dark energy drives this acceleration. It makes up about 68% of the total energy content of the cosmos. We know even less about dark energy than dark matter. We observe its effect. We see galaxies accelerating away from each other. We measure the rate of expansion increasing over time. But we cannot explain why. If dark energy continues to accelerate expansion forever, the universe faces a strange fate. Eventually, galaxies beyond our local group will recede faster than light. Their light will never reach us. The observable universe will shrink. Distant galaxies will fade and disappear from view. Trillions of years from now, observers in our galaxy will see only the local group. They will have no evidence that other galaxies ever existed. The universe will seem small and lonely, all evidence of its true vastness erased by expansion. We live in a fortunate era. We can still see the distant universe. James Webb can capture light from 13 billion years ago. The cosmic story remains readable. But this window will not stay open forever. Expansion will eventually hide most of the universe from any observer anywhere, 93 billion light-years across. 2 trillion galaxies, structures billions of light-years long, and most of it invisible, made of matter and energy we cannot explain. The true scale of the universe humbles every human ambition. We are smaller than we ever imagined. Something is wrong with the universe. The numbers do not match. 2 different ways of measuring the same thing give 2 different answers, and James Webb just confirmed that the problem is real. The universe is expanding. We have known this for nearly a century. Edwin Hubble discovered it in the 1920s when he noticed that distant galaxies are moving away from us. The farther away a galaxy is, the faster it recedes. This relationship is not random. It follows a precise mathematical pattern. A number called the Hubble constant describes this pattern. It tells us how fast galaxies move away for every unit of distance. If the Hubble constant is 70, a galaxy 1 megaparsec away recedes at 70 kilometers per second. A galaxy 2 megaparsecs away recedes at 140. The relationship is linear. Straightforward, measurable. The problem is that scientists cannot agree on what the Hubble constant actually is. There are 2 main ways to measure it. The first uses the cosmic microwave background. This is the faint glow left over from the Big Bang. It fills the entire universe as a nearly uniform sea of microwave radiation. Tiny temperature variations in this radiation carry information about the cosmos as it existed 380,000 years after the Big Bang. By analysing these variations, scientists calculate how fast the universe was expanding back then. They use mathematical models to project forward to the present day. This method gives a Hubble constant of about 67. The second method uses nearby objects. Astronomers measure distances to galaxies using stars called Cepheid variables. These stars pulse in brightness at rates directly related to their true luminosity. By comparing how bright they appear to how bright they actually are, astronomers calculate distance precisely. They also use Type 1 supernovae, which explode with consistent energy and serve as standard candles across the cosmos. By measuring how fast nearby galaxies are receding and comparing that to their distance, scientists calculate the Hubble constant directly. This method gives a value of about 73. 6 points of difference. This might sound small, it is not. Both methods are extremely precise. The uncertainty in each measurement is only about 1 point. The gap between them is 6 times larger than the error bars. This is not a rounding problem. It is not measurement noise. It is a real, persistent discrepancy that has troubled astronomers for over a decade. Scientists call it the Hubble tension. Before James Webb, some researchers hoped the problem would disappear with better data. Maybe the Hubble Space Telescope had made errors measuring Cepheid stars. Maybe something about how Hubble observed introduced a systematic bias. If the distances were slightly wrong, the local Hubble constant calculation would be wrong too. The tension might just be a mistake. James Webb tested this hope directly. It observed the same Cepheid stars Hubble measured. It used its superior infrared sensitivity to get cleaner, more precise data. If Hubble had made errors, James Webb would find different values. James Webb confirmed Hubble's measurements exactly. The distances are correct. The local Hubble constant really is about 73. The tension is not an observational error. It is real. This leaves two possibilities. Either something is wrong with our model of the universe, or something changed in how the cosmos expands over time. The standard model of cosmology assumes expansion follows a smooth, predictable pattern. It depends on the amounts of ordinary matter, and dark energy in the universe. Scientists have measured these amounts carefully using the cosmic microwave background. They plug the numbers into equations that describe cosmic evolution. The equations predict how fast the universe should expand at different times. If those assumptions are correct, both measurement methods should give the same Hubble constant. They do not. Something is missing. One idea involves dark energy. We assume dark energy has constant strength throughout cosmic history. It pushes space to expand at an accelerating rate, the same rate everywhere and always. But what if dark energy changed over time? What if it was weaker in the early universe and stronger today? This would cause the expansion rate to evolve differently than the standard model predicts. The early universe would expand at one rate. The current universe would expand at another. The two measurements would naturally disagree. This possibility is exciting and troubling. If dark energy varies, our entire understanding of cosmic evolution needs revision. The equations we use to calculate the age of the universe, the distances to galaxies, the fate of cosmic expansion, all would need adjustment. Everything we think we know about cosmology would shift. Another possibility is that the universe contains something we have not detected. A new form of energy or matter that affects expansion. Some theorists propose particles called dark radiation. Others suggest interactions between dark matter and dark energy that we have not accounted for. A few propose modifications to Einstein's general relativity itself, the fundamental theory that describes how gravity shapes spacetime. Each proposal has problems. None fully resolves the tension without creating new difficulties elsewhere. The search for an answer continues. Here is something strange that a few physicists have suggested. Perhaps the tension reveals that we live in an unusual region of the universe. Local variations in matter density might affect nearby expansion rates. Our cosmic neighborhood might be slightly underdense compared to the average, causing galaxies to recede faster than typical. This idea is controversial. Most cosmologists reject it because the universe should be statistically uniform on large scales. But the tension is stubborn. Unusual explanations remain on the table. What makes the Hubble tension so important is what it represents, a crack in the foundation of modern cosmology. Our best models of the universe, tested and refined over decades, fail to produce consistent answers for one of the most basic measurements we can make. The expansion rate of the cosmos. How fast everything is moving apart. James Webb did not solve the tension. It made the problem worse by confirming that observational errors are not responsible. The tension is real. It demands explanation. And no one has provided a satisfying one yet. This is how science works. We build models to explain observations. New observations test those models. When the models fail, we learn something profound. We discover that our understanding is incomplete, that nature has secrets we have not uncovered. The Hubble tension tells us there is something fundamental about the universe we do not yet understand. Perhaps a new form of energy. Perhaps a modification to gravity. Perhaps something stranger still. The answer waits somewhere in the data. Somewhere in the photons James Webb collects from distant galaxies and ancient light. The universe is trying to tell us something. We have not yet learned how to listen. You are made of stars. This is not poetry. It is chemistry. The iron in your blood was forged inside a massive star that exploded billions of years ago. The calcium in your bones came from supernovas. The oxygen you breathe was created through nuclear fusion in stellar cores, carbon, nitrogen, phosphorus. Every element essential to life was manufactured inside stars that lived and died long before Earth existed. The atoms in your body have travelled across the universe. They drifted through interstellar clouds. They condensed into new stars and planets. They cycled through generations of cosmic evolution spanning billions of years. Eventually, they found their way here. Into this planet. Into your body. Into the consciousness reading these words. You are the universe becoming aware of itself. James Webb has shown us where this process began. The telescope looks backward in time to epochs when the first stars ignited, when the first heavy elements were forged, when the foundations of complexity were laid in the nuclear fires of stellar cores. Every image the telescope captures connects directly to your existence. The galaxies it observes are your ancestors. The stars it detects are your origins. Consider what we have witnessed together through this journey. A golden telescope floating in permanent shadow nearly 1 million miles from home, its mirrors drinking ancient light that has travelled for over 13 billion years. Deep field images revealing 10,000 galaxies in patches of sky you could block with a grain of sand. The farthest galaxy ever confirmed, Mum Z14, shining when the universe was barely 2% of its current age. We saw the cosmic dark ages give way to the cosmic dawn, the first stars igniting in the void, light flooding a universe that had known only silence. Reionization transforming neutral hydrogen into plasma across hundreds of millions of years. The beginning of everything we now call structure. We found galaxies that formed too fast. Massive, bright, fully developed systems existing when the universe was only a few 100 million years old. Star formation efficiency that our models cannot explain. Heavy elements appearing earlier than they should. The universe building itself at speeds that mock our careful predictions. We discovered black holes that grew too large. Monsters weighing millions of solar masses appearing before there was time to grow them. Feeding rates exceeding the limits physics demands. Super Eddington accretion caught in the act. Heavy seed black holes and supermassive stars proposed as explanations, neither confirmed, both waiting for proof. We encountered little red dots scattered across the sky. Compact objects defying classification. Black holes that outweigh their galaxies. Star clusters too dense to survive. Evidence that the early universe followed different rules we have not yet decoded. We tracked a runaway black hole racing through space at 2 million miles per hour, trailing newborn stars in its wake. We observed 2 black holes spiraling toward collision, their merger destined to shake space-time with gravitational waves. We learned that the cosmos is dynamic, violent, active, never still. We confronted the true scale of everything. 93 billion light-years across. 2 trillion galaxies. 800,000 galaxies in a single deep field image. Structures stretching billions of light-years. Dark matter holding everything together while remaining invisible. Dark energy pushing everything apart while remaining unexplained. And we discovered the Hubble tension. 2 measurements of cosmic expansion that refuse to agree. A crack in the foundation of cosmology. Evidence that our understanding is incomplete. That something fundamental remains hidden. That the universe guards secrets we have not yet earned the right to know. All of this connects to you. The heavy elements created in those early galaxies eventually spread through space. They became part of later generations of stars. Some of those stars formed planets. Some of those planets developed conditions suitable for chemistry. Complex molecules assembled. Life emerged. Evolution unfolded over billions of years. Consciousness arose. And here you are. A being capable of building telescopes. Of asking questions. Of wondering what lies at the edge of observable reality. There is something deeply strange about this situation. The universe has existed for nearly 14 billion years. For most of that time, no one was watching. Stars formed and died without observers. Galaxies collided without witnesses. Black holes consumed matter in absolute darkness. Then, in the last fraction of cosmic history, minds appeared. Beings who could look up and ask why, who could build instruments to extend their vision across billions of light years, who could reconstruct the story of creation from photons that left their sources before Earth existed. You are living in the first generation of humans to see the early universe directly. Your ancestors looked at the same sky but saw only points of light. They imagined myths to explain what they could not understand. Now we have James Webb. Now we have spectra and redshifts and deep field images. Now we can witness the cosmic dawn with our own technology, if not our own eyes. This is extraordinary. This is unprecedented. In all of cosmic history, this moment is unique. The universe has become able to study itself through you. Let that settle into your mind as your body relaxes, as your breathing slows, as the weight of the day releases from your muscles. You carry stardust in your veins. You carry the legacy of supernovas in your cells. You are not separate from the universe James Webb observes. You are part of it, a continuation of processes that began billions of years before your birth. The telescope will continue its work. More distant galaxies await discovery. More impossible black holes will challenge our theories. More little red dots will scatter across new images. The Hubble tension may find resolution, or may deepen into something stranger still. Science moves forward, question by question, photon by photon. But you do not need to carry this journey any further tonight. The universe is vast beyond imagination. It stretches 93 billion light-years in every direction. It contains 2 trillion galaxies and more stars than grains of sand on every beach on Earth. It holds mysteries we may never solve and wonders we have not yet glimpsed. All of it continues whether you are awake or asleep. So let go. Let your thoughts drift like galaxies through the void. Let your awareness expand like space itself, soft and boundless. The cosmos has been here for nearly 14 billion years. It will be here when you wake. The stars will still shine. The photons will still travel. James Webb will still gather light from the edge of time. You have journeyed far enough tonight. From a telescope floating in shadow to galaxies at the dawn of creation. From black holes breaking the laws of physics to the true scale of everything that exists. From cosmic mysteries to the stardust in your own body. Now rest. Let the universe hold you. You belong to it, and it belongs to you. Sleep well, knowing that somewhere in the darkness, ancient light is still falling toward golden mirrors, still carrying stories from the beginning, still waiting to be seen. The cosmos dreams through you. Close your eyes